I will begin the record. Okay, the record is on. Hello everyone, welcome to the third webinar organized by EUROfusion. I am France Boileau-Cerneux, I work at CEA and I am the chair of this webinar. So today we have an introduction to Kokkos and the talk is given by Thomas Padioleau at Maison de la Simulation. Thomas, you can go.
Thank you, France. So, welcome to all of you. So, I'm Thomas Padioleau. I'm a PhD student at Maison de la Simulation. So, thank you for giving me this opportunity to introduce Kokkos. So, here is the outline of my presentation. So, I will start by introducing the performance portability problematic. Then I will introduce the Kokkos library with some examples. And finally, I will end with my user experience. So, as you may know, Moore's law is an economic empirical law which predicts that the number of transistors should double every 18 months, roughly. So as you can see on this picture, there is the transistor count in orange points in function of time. So the evolution of CPUs can be divided roughly into two periods. The first period until the beginning of 2000, the power, the computational power was increased due to an increase of frequency. And in a second time, because of reaching the heat wall, manufacturers had to divide CPUs into cores, reaching right now around hundreds of cores on a single chip. This led to the development of shared memory parallelism on a single node, single CPU. And so the goal was to find more parallelism, fine-grained parallelism in algorithms. This also led to the usage of GPUs, which are architectures which natively handle massive parallelism at the beginning of around 2010 with the introduction of the CUDA by NVIDIA. So if we have a look now at the recent top 500, which is a ranking of the most powerful supercomputers in the world, we can see that there is some diversity between among architectures. The first rank is attributed to Fugaku in Japan, which is an ARM-based architecture. We have in this top 8, which I'm showing, 4 GPU machine here with NVIDIA V100 architecture and other mini-core CPUs from China and Intel. So among this diversity, we can see some trends among supercomputers. The fact that nodes are getting fat and heterogeneous. So if we have a look here at the drawing on the right-hand side, we have a chip which is made of many cores. These cores communicate between each other using a network on chip. This chip has on-package memory, may have a usual central memory. This chip can be to this chip can be added accelerators, which have also their own on-package memory. So to target all of these architectures, we need different programming models. Usually OpenMP, OpenACC, CUDA, and others. And we also need to prepare for future architectures which are coming. So we need some abstraction layer to avoid re-implementing and to ease maintainability of codes. And so this is for the portability issue. But we also want performance. So we need abstraction that is able to handle performance. So here are some examples of strategies to perform this performance portability. So this is clearly a non-exhaustive list. And this is divided into 4 categories here. So the first category would be simply duplication of code. So the end user has to implement, if it has one algorithm, it has to implement different version of it to reach portability and to reach performance on the targeted architecture. So we can think of CUDA, OpenMP, pthreads. A second category would be directive-based models or pragma-based models, like for example OpenMP4 or OpenACC, in which you write a sequential code at first, then you decorate it with pragma. You decorate loops with pragmas, which can generate different binary codes depending on the architecture. So this has the advantage of to be not that much intrusive into the code. These pragmas can be disabled if you want to get rid of it. But it doesn't force you to think of the implementation as parallel at first. Third category would be frameworks, or DSL for domain-specific languages. So there is a long list. I mentioned some libraries like Trilinos, AMRX, or FFTW. So these libraries provide you algorithms, so high-level algorithms, and these libraries handle the portability issue, maybe with some of these other categories. And so the end user doesn't have to manage the parallelism. And the final category would be libraries, mainly written in C or C++, in which there is Kokkos, so the topic of today, Raja, Alpaca, and Cycle implementations. So Cycle is a standard provided by Khronos, and there are some implementations of it, like for example the Intel DPC++, which is quite recent. So what is Kokkos? So Kokkos is a library, C++ library. It implements a programming model to write performance portable software, so both portable and performant. It was extracted from the Trilinos library, which was at the low level and still is, but it is an independent project to be able to target different codes inside Sandia or outside. It relies on advanced C++ features such as template metaprogramming and function objects. So as an end user, and at first you don't have to be an expert on template metaprogramming, but still you have to have some strong knowledge of C++ like function objects. It uses existing shared memory programming models such as OpenMP, pthreads, CUDA. For now, it relies for vectorization on auto-vectorization such as the pragmas. And there is an intrinsics wrapper which is in development. Some more programming models were announced, such as AMD GPUs and Intel GPUs, which are coming for the next Aurora machine. There is also an effort from the Kokkos team to contribute to the C++ standards So there is an effort to port their own container, which I will present after, the Kokkos view, which will be in the standard named as std MD-span, which is a multidimensional container. So, as I said, Kokkos implements a programming model. So there are many concepts that were introduced in this and which are necessary to handle different aspects of heterogeneous computation. So here it is divided into two categories. In blue, what is related to the execution of an algorithm, and in green, what is related to data management. Because when you have different devices on a single node, you need to specify where your data reside and where your computation takes place. So the first, so if we begin with execution, the end user of the Kokkos library has to implement its own algorithm based on basic algorithm that Kokkos provides, such as parallel for, parallel reduce, parallel scan, and parallel task. So I've been mainly using parallel for and parallel reduce, not that much parallel scan, and not at all parallel task. Once you have chosen your basic algorithm, you have to say where the computation should take place. So depending on the compile options and some runtime choices, you can choose where your algorithm will be executed. You can also provide some execution policy, so how computation should be executed. Depending on the architecture, you may, or depending on the algorithm, you may want to choose different execution policies. Your algorithm should act on some data, and you have to specify, you have the possibility to specify where your data reside, on which, if it is on the CPU or the host, which refers to CPU, or like on the GPU. Kokkos provides, as I said, its own container. It is a multidimensional container. There in C++ or even in C, there is no native such container, no multidimensional container. As it is multidimensional, you can have a choice of the layout, of the memory layout. Internally, the memory is contiguous, so you have to choose how to map this contiguous memory into a multidimensional index. And you can specify some memory threads, which is specifying how you access your memory, if it is atomic, random access, read-only access. So this is simple example of this code doesn't do anything interesting, but this shows you how to get from a sequential code to a version of Kokkos version of it. So on the left-hand side, we have the main function of a C or C++ program, in which we defined an array made of a two-dimensional array, which has a compile time dimension and a runtime dimension. So we create this array and we loop over it using native loops of C++ language. So this is prescribing the fact that we iterate from 0 to nx in increasing order, and we assign values to this array. On the right-hand side, we have the Kokkos version of it. So all Kokkos-related functions are in the Kokkos namespace, and we begin with initialization of the library, which also handles finalization, because it is the finalization of the library is done at the destruction of this object. Here again, we define the two dimensions of the array. And here we switch to the Kokkos container, Kokkos view. I will give more details in the next slide. So we have to specify some template parameters. And once this array is defined, so a difference between the two examples is here that we specify here that the one dimension is known at compile time, the size of it is known at compile time, and the other is only known at runtime. Then here we don't prescribe how to do the computation, but we only describe that we want a parallel for execution. So we want to range from 0 to nx, and again we assign values to this array using the function call operator of the object. So this simple code can be compiled for GPUs, so for NVIDIA GPUs and CPUs, and can run in this loop can run in parallel compared to this first example, so the left-hand side code. So now let's go back to the Kokkos view, and I will give some explanations of it. So the view is a class, a template class, that you have to specify some template parameters. The required template parameter that you need to provide is the data type. So the first, in this example, we specify that we want a two-dimensional array. This is provided here by the 2 stars. And the data type here is double. So even if there are 2 stars, internally the array is stored as a contiguous array. We can choose the layout, and we can choose the memory space. It is not required. We can rely on some default values which provide Kokkos, which are provided by Kokkos. We can provide some memory threads. I will not cover this today. One important fact is the way of copying such containers. So there are 2 ways of copying. One way is using the assignment operator. So here in this example, if A and B are both compatible Kokkos views, you can assign B to A. It means that A will refer to the same memory location as B. In the second, you can also deep copy. It means that both A and B refer to different memory locations, but you want that A has the same values as B. So there is a real memory transfer here between maybe a GPU and a CPU, or CPU to CPU, or GPU to GPU. They also provide some mirroring between host and device, which is the copying, and which is free if the node you are running on doesn't have GPU. So this won't copy, as they will both views will refer to the same memory location. So as I said, as a template argument, you can also specify the layout. Kokkos provides two layouts, left and right, which refer to row major and column major orders. And if you need some extra or more complex layout, you can provide your own layout using this template parameter. So that was for memory. If we go back now to execution policies, so you specify in a parallel in an algorithm how you want to execute your kernel. As I said, there are three types of execution policies that I will cover: range policy, multidimensional range policy, and team policy. So we begin with range policy. Here we implement a kernel, so a function object to be more precise. So this is a class which implements the function call operator. This function call operator takes as an argument an integer. This integer is given by Kokkos in the parallel for when the algorithm is executed. So you have to provide, this is the kernel, you have to provide this body. So in this example, we use this linear index. We unlinearize it to do some stencil computation using Kokkos views, which are stored as member attributes of kernel A. So we pass Kokkos views by copy and store it in the member attributes. So the range policy is going from 0 to nx times ny to cover all points. A more suited to stencil computation would be the multidimensional range policy. Here we take A and B as two-dimensional, there are two stars, two-dimensional Kokkos views. And this time the function call operator is taking two integers as input parameters. And you can see that the kernel is writing is simpler than in the previous case because of the usage of this two-dimensional range policy and the two-dimensional Kokkos view. And as a final example of execution policy, there is the team policy. Here again, we take two Kokkos views, two-dimensional Kokkos views. But here in this time, we have a custom type from Kokkos instead of a simple integer. So in this policy, we can express hierarchical parallelism. In previous examples, we could not have parallel for a call of parallel for inside the function call operator of the kernel. This time we can by using the team input parameter. So in this team policy, there are three levels of parallelism. So we have a league which is made of teams. Teams are made of threads, and threads are made of lanes. So these three levels map to some hardware resources, and we can use it to map work to them. So in this example, we map some thread inside a team to a row of points. And we distribute the work to one thread here. So this example is a bit more complicated, but it gave a better result, as I will show you. So I've used this library in my PhD to do some hydrodynamics simulations. So solving Euler equations with diffusive fluxes and some source terms such as gravity, and for two-phase flow simulations using 5 equations model. So both are solved using finite volume discretization on a uniform mesh, which gives which is an easy case for parallelism. So here on the right hand side, you can see the impact of a droplet, of liquid droplets onto a wall, which correspond to this type of simulation. So we have tried different strategies related to execution policies that I showed you earlier. We first tried the range policy, which was quite easy to use, even though you have to manually unlinearize the index. It gave good performance on GPU because it would have been close to a CUDA implementation of the kernel. But on CPU, it gave quite bad results due to a lack of vectorization, mainly on a KNL, Intel KNL architecture. So because of some if conditions inside the most inner loop, it was not able to recognize vectorization. The second strategy has been to try the MD range policy. It was also easy to use, even if it leads to duplication of codes using 2D and 3D versions. But it gave also bad performance on GPU and CPU. Kokkos developers knew that when we met them. I don't know if it evolved since then. And finally, we tried the hierarchical parallelism, which gave the best results. So the idea was to expose the most inner loop to get vectorization without losing good result that we have with the range policy. So it was a bit more complicated, but a bit more also closer to hardware resources and gave good results, as I can show you here. So the metric here is the number of million cell of dates per second. So the first version was using, in our code called ARC, was using range policy. So here we have the performance of different architectures. So mainly NVIDIA, so GPU, and Intel KNL, which was the most critic. And we see that we have a big gap between Intel KNL and NVIDIA V100s, and no difference between vectorized and not vectorized code. When going to the team policy, execution policy, we could recover some performance. So this is logarithmic scale. We could recover some good performance on the Intel KNL architecture. You can see here a gap of a factor between 6 and 8 between the vectorized and unvectorized version, without, as I said, losing performance on the GPU. So this was a good result for us. As I also said, Kokkos only provides shared memory parallelism. So using to target supercomputers, you also need to go to multiple nodes. So we used an hybrid parallelism using MPI plus Kokkos. The general idea would be to use MPI to go to multiple nodes and to let Kokkos use the shared memory parallelism inside a node. In practice, we use one MPI process per NUMA region, and Kokkos doesn't handle multiple GPUs. So you have to use one MPI process per GPU if you want to use, let's say, up to 4 GPUs on a node. So thank you for your attention, and I will answer questions if you have any.
Thank you very much, Thomas, for the presentation and the introduction to Kokkos. Guys, do you have any question? I don't see any questions in the chat. So please raise your hand. Actually, I have one question, Thomas. So I'm quite
Yes.
beginner with Kokkos. Is there a link with Kokkos and Trilinos? Like, to me, Trilinos is proposing kind of packages like for linear eigensolver, stuff like that. So is there a link between the two?
Yes. So Trilinos at first was including Kokkos, and Kokkos was only in was not an independent project. But as of now, there are these are two different projects, and Trilinos is relying on Kokkos to implement some basic linear algebra operations.
Okay, so basically,
So they.
okay.
Yeah.
Okay, thank you, Thomas. I see one question from Thomas Hayard. Okay, the question is, what was the state of the code before you starting editing Kokkos? A C++ code with some intranode parallelism already included. Thomas Hayard, if you want to unmute, you can.
So I started with an existing code which already implemented, if you may know, Maison-Koch numerical scheme for hydrodynamics equations, and with MPI. So it was using range policy. And so I tried the different execution policies to see what was giving the best results. So there are some basic examples on the Kokkos repository. There is a tutorial if people are interested.
Thank you, Thomas. Guys, is there any other question? Yep, Thiago. Do you have any experience with other libraries like DPC++? How do they compare?
So I haven't any experience with other libraries. I know that they're really similar. They so I can go back to so as I said, there is Kokkos, Raja, Alpaca. They all try to give abstract notions of execution of to get some abstract notions on architectures to provide you performance portability. Cycle implementations are much more general than just what people at Sandia try to target. They mainly target their own applications. An example would be Trilinos, but they also have other internal codes. And as I know, Cycle, so there is a comparison here, there is a link. They also claim that as they want to be more general, they won't give you some patterns like parallel reduce, which can be tricky to implement on some architectures. So Kokkos provides it, and Cycle doesn't.
Okay, thank you, Thomas. We have a question from Jacques David. Okay, Jacques is saying, I understand there are different backends possible. You showed only one, NVIDIA CUDA. Do you have any experience with other backends, Thomas?
Okay. So I don't have experience on the Rocken. But I have experience on Intel KNL and Intel Skylake, and we also did the Grand Challenge on AMD machine at TGCC. So we have good results in our code using the team policy. But for a GPU, I have only one experience with NVIDIA GPUs.
Jacques is also asking, how do you
Yes.
profile your code? What tools do you use? Is it NVIDIA tools?
No, we don't go that far. We only have this metric, the number of cells updated per second.
And do you know about an existing tool to profile or specific to code?
So they provide what they call connectors. So the Kokkos team provides connectors to some existing vendor softwares such as NVIDIA profilers or Intel profilers.
So I guess
if,
the same
if people are...
Oh, sorry, go ahead.
Sorry?
I was asking, I guess it's the same for debug?
For debug, as far as I know, you are on your own.
Okay.
But there is quite large community, so you can ask for help if you have questions.
Okay. Thank you, Thomas. Do we have any other question for Thomas? Okay, I guess it's a no. If I have a question in the meantime, I will send it to you, Thomas. Thank you very much for the presentation, Thomas, and answering the question. We really appreciate. Thank you, everyone, for attending, and I think we can close the webinar. Just one quick point. Next webinar will be in September. There is no webinar in August. So have a great summer and see you in September. Bye, everyone.
Thank you.
Thank you, Thomas.